This program is brought to you by Stanford University.
Maybe you could say what omega is, too. You see that?
Oh, omega, big omega.
Yeah, big
Yes.
omega.
Yeah. Right. Okay, so you asked me what omega is, and omega is an important quantity, so let's discuss it. You go back to the Friedmann-Robertson-Walker equations, and those have the form A dot over A squared. We know about that. And on the right-hand side, we have various things. We could have a vacuum energy. Let's talk about today, or at least for an era well after the radiation-dominated era ended, at the time, which includes the present today, when the equation of state, I'll just wait a minute. I'll wait a minute. All right, so somebody asked me what capital omega, now there are several capital omegas, incidentally. One of them simply represents the sphere, the two-sphere or the three-sphere. That's a different omega. In cosmology, there is another omega, which has to do with the percentage of matter, or the percentage of energy in different forms, that come in different forms. Okay, so that's the percentage of the energy that goes on the right-hand side of the expansion equation, the Friedmann-Robertson-Walker equation. The left-hand side, of course, is the Hubble constant, or the Hubble parameter squared. The right-hand side can contain, first of all, a vacuum energy. Let's see, it's not called, we shouldn't call it lambda. Rho naught, 8 pi g, over 3 times the vacuum energy. Then, if we're talking about the era, which includes today, when radiation was not very important, and in which mostly the energy density of the universe, apart from the vacuum energy, is dominated by ordinary, non-relativistic, slowly moving objects, such as galaxies. Then there's another term in here, which is, let's say, rho matter. It also multiplies the 8 pi g over 3. So let's put a bracket around it. The vacuum energy. The part which doesn't change with expansion. And that, of course, just to remind you, this part here is some constant, let's call it m divided by a cubed, so it dilutes with expansion. There might also be a radiation part, but let's ignore it. It's very, very small. After the period when the universe was very, very hot, when it cooled below the temperature of the sun, let's say, radiation was not so important, and the matter part of the energy density was the important part. And let's see, is there anything we're missing? Yeah, we're missing plus 1 over, or plus k, or minus k over a squared. That's the curvature part. That's the part which is k equals plus 1 for a positively curved universe, k equals minus 1 for a negatively curved universe, and k equals 0 for a flat universe. Let's mostly concentrate on, for the moment, on the flat universe. Then all omega is it's the fraction of energy, well, let's put it this way, yeah. It's just a fraction of energy carried by the different components, okay? It must add up to 1 for the simple reason that, sorry, I'm saying it not quite right. I'm saying it not quite right. All right. Yeah. What I want to do is get rid of this and put it over on the other side. 3 over 8 pi g. Let's get rid of it over here. And let's forget this for the moment. Now, these two have to add up to this. This is the square of the Hubble constant. They've got to add up to this, but not if k is anything, is either plus 1 or minus 1. If k is plus 1 or minus 1, they don't quite have to add up to the left-hand side here. Right? The thing to do, to understand this, the thing to do is to divide this equation by what's on the left-hand side. Let's just simplify it and call it Hubble squared. This is the 8 pi 3 over g, but let's ignore that for the sake of argument for here. It's just Hubble squared times a number, and that's equal to the sum of 3 terms. Here's the way to think about it. It's the sum of 3 terms. Rho naught plus rho matter minus k over a squared. And this is either plus 1 over a squared or minus 1 over a squared or whichever, and then divide it by Hubble squared. Divide it by Hubble squared. 1 divided by Hubble squared, divided by Hubble squared, divided by Hubble squared. These things have to add up to 1. That's just trivial. I just divided by the left-hand side of the equation to get 1 here. All right? But notice, that's not the only thing we could say. We can say if k is equal to 0, these two things have to add up to 1. The energy density in the vacuum together with the energy density in matter must add up to 1. Otherwise, space can't be flat. Now, first of all, since rho naught and rho matter vary differently with time, there's no way that this can be constant. So the only way you can have it add up to 1 is if rho matter over h squared, if there's no rho naught, if h were constant. But h is not constant. H is not constant in general. And since h is not constant in general, there's really no reason why this cannot add up to 1 in general if h is varying with time. So because h varies with time, rho naught over rho matter over h squared could add up to 1. But it can only add up to 1 if k is equal to 0. That's what the equations tell you. That if rho naught plus rho matter over h squared add up to 1, then what do? You measure the different components of the energy, you add them up, you divide by the observed Hubble constant squared, and here's a prediction. If space is flat, if this is not important, then these have to add up to 1. The energy density, or the vacuum energy density plus the matter energy density divided by the square of the observed Hubble constant must add up to 1. Now these things, this is called omega. This is called omega. And the first term here is called omega 0, or sometimes omega vacuum, or sometimes omega lambda to stand for cosmological constant. And the second term here is just called omega matter. Rho divided by h squared is called omega. Okay? Now, first conclusion is if space is flat, omega naught plus omega m must add up to 1. So in that sense, if k is equal to 0, omega naught and omega matter are simply the fraction of energy carried by either vacuum energy or matter energy. That's what they are. They can change with time, but they have to change with time in such a way as to add up to 1. But if, on the other hand, space is curved, if space is curved, then we can put on the right-hand side 1 plus k over a squared, h squared, and then the sums of the omegas do not have to exactly add up to 1. Okay? Adding them up, and let me remind you what this means. You first measure to the best of your ability, astronomically in various ways. You measure the vacuum energy, you measure the matter energy, and you divide it by Hubble squared, the sum. The sum may or may not add up to 1. If it adds up to 1, that's an indication that space is flat. So when people say space is flat, it implies that the sum of these two have to add up to 1, and in that case they really are just a fraction of energy carried by matter and by vacuum. Okay? If these two don't quite add up to 1, for example, if they add up to something bigger than 1, that says that k is positive. It implies that the universe must be positively curved. So if you measure Hubble and you measure rho, and the ratio is bigger than 1, then space must be positively curved. If it's less than 1, then k must be negative and space must be negatively curved. So this is what omega is. Omega is a measure, yeah.
Does matter include dark matter?
Yes, it includes dark matter.
And anything else besides just dark matter and regular old particles, any kind of...
Yeah, well, we could add in here rho radiation, but it's such a small fraction that it doesn't matter. So in practice, it's just matter and vacuum. Yeah.
Is there some measure of dark energy other than the Hubble constant?
The Hubble constant itself is not a measure of dark energy. It's the way that the Hubble constant changes with time. The fact that it doesn't seem to be changing with time, which is the indication of dark matter.
No, I mean dark energy.
Dark energy, yeah. The fact that the time rate of change of the Hubble constant is decreased, which is the same thing as saying that we're on this branch of exponential expansion. In other words, if A dot over A is becoming constant, that's equivalent to saying A is exponentially increasing. So the observed apparent tendency toward exponential increase is the direct evidence for rho naught. Okay. Okay.
But isn't that the same thing as indicate, I mean, how is that separate from H?
Well, okay. It's not. It's not. You're asking observationally, how do you tell the difference? Observationally, what you actually measure is K.
Why?
What you actually measure is K, and K tells you what rho naught is. Observationally, you measure the fact, geometrically, we haven't had a chance to get into this, but geometrically you measure the fact that on large scales space is flat. That tells you that K is equal to 0. Once you know K is equal to 0, and you have also measured the matter energy, then you know what rho naught has to be. Given now that you know what rho naught is, you can then predict the way the universe expands with time. You find out that it's not 0, and it says that it's accelerated. So there is a prediction in there. From the fact that space looks flat, it tells you that rho naught, or that,
Tells you rho naught from the other.
yeah. This you measure. That's, yeah. You measure this by measuring the ordinary material in the universe that you can see, plus the part that you can't see, which is the dark matter, which you measure gravitationally by the orbits of stars around galaxies.
Well, now we have like 3 different ways to measure them.
Yeah, that's right. We have several different ways to measure this, several ways to measure this. They're both measured, and they add up to something close to 1. Sorry, yes, they add up to something. No, they add up to something. We also measure the Hubble constant, and it all adds up. But on top of that, the measurement of the curvature itself is equal to 0.
So you solve for rho 0 in there.
Yeah. So we have some cross checks. There are various cross checks, and the cross checks involve the acceleration of the universe, which tells us that, the direct measurement of matter and dark matter, which tells us that, the direct measure of the Hubble constant, which just looks out to different distant galaxies and tells you how fast they're moving. Indeed, they add up to about 1, and that tells us that space ought to be flat. And then you measure the curvature of space by triangulating it, and you find that it's flat. Okay, to a good approximation. So, so those are the pieces of evidence that are telling us that however we got that way, we don't know, but space is very, very flat to a couple of percent. Why is it so flat? Well, the theory is that it inflated. Being flat just means it's very big. It's very big and very smooth. Very big and very smooth and very homogeneous. On scales, how big? On scales of billions of light years. On scales of billions of light years, in fact, really tens of billions of light years, it's very flat, very homogeneous. How did it get that way? The speculation or the conjecture, and by now it's more than a conjecture, there's good empirical evidence for it, that the universe underwent in a very early period, before what we normally call a Big Bang, the universe underwent a period of exponential expansion, and that exponential expansion just stretched it out so much that it appeared very, very flat. Now you can overdo a good thing. The universe is very flat, and at the time of the Big Bang it was very smooth, but if it were perfectly smooth, if it had been perfectly smooth, then there would be no way for structure to form. A perfectly smooth universe, one which is perfectly symmetric, will stay perfectly symmetric. The equations of gravity and so forth will not create lumpiness out of perfect smoothness. And so we know that the universe wasn't perfectly smooth. And if we trace backward from the current knowledge of galaxies and the current knowledge of the degree to which the universe is not homogeneous, if we trace that backward, we find out that at the time when the universe first became transparent, at the time that radiation decoupled from matter and so forth, the time that we normally call the Big Bang, there was something like about 1 part in 10 to the 5th anisotropy and inhomogeneity. That means if we were to have plotted at that time the energy density or mass density as a function of position, we would have found that it's very, very constant, almost perfectly flat, but, and of course I can't draw this on the blackboard, with about 1 part in 10 to the 5th, there was a bit of wiggliness in it. Wiggliness in it at different scales. That wiggliness, now that's much, much smaller than the current. By now, stuff is concentrated into galaxies, and it's highly inhomogeneous on small scales. So what happened, and this is something that we can follow, starting with this primordial little bit of fluctuation. Where it came from, we have some ideas, but where it came from, we don't ask at the moment. We say, supposing it was there, what happened next? Well, the little overdensities, these are regions of overdensity. They were surrounded by regions of underdensity. Let's draw those dotted. And then other regions of overdensity and so forth. Other regions of overdensity. The regions of overdensity gravitated and pulled things toward them. In fact, they pulled the matter immediately in between these two regions into the two regions, increased the overdensity, and increased the magnitude of the underdensity. So it's a sort of self-reinforcing feedback that the more inhomogeneity you have, the more gravity will lead it to become yet more inhomogeneous. Right? This is different than the air in this room. If we created a perturbation in the air in the room, a little wave-like disturbance, that wave-like disturbance will eventually disappear. It'll disappear, it'll come to thermal equilibrium, and the room will again become homogeneous in its content of air, okay, for example. So gravity is different than other forces. It tends to lead to this instability where a little overdensity will increase itself. In fact, if you just took a completely homogeneous universe and put in just a little bit of overdensity, it would start sucking the material from nearby and create an underdensity. The underdensity would start to grow, and the overdensity would start to grow, and eventually the thing would collapse and form perhaps a galaxy. Yeah?
Why didn't gravity do that before that?
Ah, that's a good question. Okay, that's a good question. That is a good question. Why did it happen at the time that radiation became unimportant compared to the other? All right. The reason has to do with pressure. Remember, we talked about the relation between pressure and energy density. I wrote on the blackboard. Pressure is equal to something called W. W is just a parameter, times the energy density. I think I called it epsilon. Does anybody remember what I called it? The density of energy? Rho, maybe rho. Yeah, we called it rho. Sure we did. Okay, so let's see how much you can remember. Okay, for radiation, what is W? Ordinary radiation, electromagnetic radiation filling a room. This room is not filled with electromagnetic radiation. It's mainly filled with atoms. But black body radiation. For black body radiation, the pressure, this is not momentum, it's pressure. Anybody remember the formula? 1/3. All right. The energy density was pretty high, and therefore, at that early time, and therefore there was a good deal of pressure. What positive pressure does is it tends to do exactly what happens in this room. Positive pressure tends to homogenize things if there's positive pressure. Positive pressure is good for homogenizing things. It pushes everything out and tends to create a homogeneous background. That's in fact why the air in the room is homogeneous to positive pressure. Now, what about matter-dominated? Or before we do that, what about vacuum-dominated? Anybody remember vacuum-dominated?
-1.
Yeah, -1. But I just asked you that to see if you remember. All right, but what about matter-dominated? 0. No pressure at all. That means that if there was no pressure whatever in this room, and there was no gravity. Let's start with no pressure and no gravity. If there were no pressure, in other words, if the air molecules exerted no pressure, how could that be? What would it take for the molecules to exert no pressure? They would have to have zero velocity, right? Zero velocity. They'd be standing perfectly still. Obviously, if they stand perfectly still and you create a bit of inhomogeneity, it's just frozen in. It doesn't do anything. Why? Because the molecules are standing perfectly still. P equals 0 means everything's standing still. But now, let's add a little bit of gravity on top of that. If we add a little bit of gravity on top of that, then the standing still is not enough to overcome the tendency of gravity to pull things toward the center. So it's a kind of competition, gravity versus pressure. Pressure keeps things from imploding. Gravity can overcome pressure if it's strong enough and cause something to implode. Now, very simply, during the radiation-dominated era, the pressure was so high that it simply prevented the gravity from doing its work and causing implosion. Radiation pressure was very high, and it just prevented lumps from forming in the same way that it does in this room here. Eventually, the radiation pressure became negligible. The pressure due to the motion of galaxies, the motion of other things, was also negligible, and gravity became the most important part. Gravity became more important than the pressure, and at that point, stuff started to contract. Yeah.
So that was before the 60. Don't you need a dissipation mechanism to have?
Yes. Well, actually, you need a dissipation mechanism to cause the ordinary baryonic matter to collide, not to have the dark matter create halos. So the first thing that happened is the dark matter, the fluctuations in the dark matter, and the fact that the pressure was so small started to create lumps of dark matter. Now, the dark matter created lumps, and the ordinary matter sort of followed those lumps. But then the dissipative mechanisms caused the ordinary matter to start to collect near the center of those lumps, and the dark matter didn't dissipate, so it just stayed there, out there as big halos. So you don't need dissipation. You don't need, I know what you're thinking. I know what you're thinking. There's a form of dissipation in cosmology, which I was going to talk about in a few minutes. There's a form of dissipation in cosmology which doesn't have to do with the normal things. It has to do with expansion. Expansion creates its own kind of dissipation. The expansion replaced dissipation. Yeah.
Since the dark matter is effectively an ideal gas,
Yeah.
if we could
It's an ideal gas at 0 temperature.
would we still see it in its original configuration?
No. Here was its original configuration, and gravity started it moving a little bit. Gravity started it condensing into lumps.
But its potential energy can't go anywhere.
Well, expansion eats up the I was going to talk a little bit about the relationship between dissipation and expansion, and we'll see it because we'll need it for something else. But just in an expanding time-dependent universe, you don't need dissipation to slow things down. So we'll come to it.
Was the dark matter, did the dark matter exist when there was nothing but energy? Is dark matter,
What do you mean nothing but energy? All there ever is energy
you know,
of various
Big
forms.
Bang, when there was this
You mean radiation energy?
radiation energy?
Yeah.
Was dark matter there, or
Yeah.
did it come out of that radiation?
No, it was there.
It was there.
Yeah. In fact, there are two time scales which are close to each other but not exactly the same. There's the time scale, or the time, at which the universe became transparent. Right? And there's a separate time scale, which is the time scale when the matter energy density, in other words, the non-relativistic dark matter, that energy density became larger than the radiation energy. Those are two crossover points. One of them is a place where it cooled enough for atoms to recombine, and the other is a place where the matter density in the dark matter exceeded the radiation pressure and allowed contraction to start happening. The contraction started happening a little bit before, maybe a factor of 10 in time. That sounds like that is a little bit on the scale of these things. Happened a little bit before the universe became transparent. So unfortunately, we can't look back to it. Been a little bit before, the universe was maybe another factor of 10 smaller. That the gravity started to do its work on the dark matter. If the dark matter hadn't been there and it was only ordinary matter, then the start of the contracting phase, not the contraction of the universe, but the contraction of these lumps, would have happened about the same time, just more or less accidentally, about the same time that the universe became transparent. And we might have been able to look back and actually see it happening, but we can't. So it's the dark matter which provides. Yeah, one or two more questions, and then I want to, yeah.
When in the chronology that you've given us did the elements greater than helium develop?
The elements greater than helium developed inside stars, for the most part. The reason I haven't talked about it very much is because it's not really considered, to a certain extent, part of ordinary cosmology. It happened too late. It's really part of astrophysics. It's really part of the dynamics of stars. Almost all of the heavy elements, except for a tiny, tiny bit, which was produced during the Big Bang. You never say none. I mean, never say never. But during the Big Bang, virtually nothing but hydrogen and helium were produced. Oh yeah, a bit of, well, that's a form of hydrogen. Yeah, right. A bit of deuterium, hydrogen, and helium. Everything else was almost completely negligible, although little trace bits of it. The actual current abundance of it was mainly made during the stellar evolution in thermonuclear processes. So, in some sense, it's not considered part of cosmology. It's part of astrophysics. That's probably taking a narrow view of cosmology. Yeah.
In addition to the inhomogeneity position, there also had to be a little in motion, so the galaxies would have angular momentum as they compacted.
Oh, they also had some angular momentum. Yeah, but that was just inherited from these fluctuations that they started with.
But those are density fluctuations.
Those were density fluctuations, but they also had some motion. There was also velocity fluctuations, density and velocity. And what we actually see in the sky is temperature fluctuations across the sky, which are remnants of these little bits of overdensity and underdensity, and also a little bit of their motion. The motion of the gas at that time, either toward us or away from us, also tended to produce some variation in the apparent temperature on the sky. So let's just remember, I mean, we look way far out to the surface of last scattering, and some of that surface of last scattering is a little bit overdense, some of it is a little underdense. The overdense regions tend to look a little bit hotter to us. No, the overdense regions tend to look a little bit colder to us, excuse me. The reason is because the overdense regions have a little more mass, they have a little more gravity, and because they have gravity, the photons that come from them are somewhat redshifted more than they would be from the other regions. So from the overdense region, where gravity is a little bit stronger, it's pulling the photons back. So what we see looking from here, the overdense regions, the photons look a little bit less energetic. From the underdense regions, they look a little bit extra energetic. But there's also another thing going on. This gas is in motion. Some of the motion may be toward us or away from us, so there's also a bit of Doppler shift. And the Doppler shift also, things which are moving toward us look hotter, things which are moving away from us look colder. All of this gets folded in, and it's complicated, difficult numerical calculations to start with a given initial condition and to evaluate what flows out of that. Experts do that. And the conclusion, basic conclusion, was at the time that the universe became transparent, or even a little before that, there was about 1 part in 10 to the 5th variation in the energy density of the universe. So on the one hand, it was very, very smooth. It was also, the universe is also known to be very flat. So it appears as if it had expanded a great deal. But on the other hand, if it had expanded infinitely, you might have thought that it would iron out these variations here. So could it be that these variations are due to the fact that it didn't grow by an enormous amount? Well, I wish that were the case, but it's not the case. These fluctuations are there because of quantum mechanics. They're remnants of quantum mechanics, and they would be there even if the universe had expanded by an infinite amount, or infinite, of course, is silly. Even if it had expanded by 10 to the 10 to the 10 to the 10 to the 10th, that would not have erased these fluctuations. Those fluctuations would have been created anew by quantum mechanics. So I thought we would talk about that a little bit and get into a little bit why it is that people believe this crazy theory that the universe exponentially expanded. And remember what it took.
Who doesn't believe it?
What's that?
Who doesn't believe
I don't know. There are from time to time people who will put forward other ideas. And usually the excuse is, well, it's just another idea with, to provide a straw man. In other words, a foil, yeah. Right. I don't know anybody who doesn't believe it. That may be a bad sign that there's too many people believing, too many believers. You know, I have my friend Don Page, who is a evangelical Christian. He's also a very famous physicist and a great one. And we argue all the time about whether such things as whether Jesus can be proved to be the Son of God and so forth. And one of his arguments is, how could so many people believe it if it weren't true? I mean, so maybe inflation is like that. I don't know. I don't think so. I think there's some spectacular empirical success of the idea. But in order to tell you what that empirical success is, I have to tell you a little bit more about it. All right. Let's remember. The idea starts with the existence of a scalar field. And it's a scalar field that has a potential energy, which is just a function of the field strength. All right? So we have a phi, which is some scalar field. What it's doing there and how it comes into the physics of particle physics and so forth is unknown. It's some scalar field called phi, and it's there for no other purpose other than to provide some vacuum energy. The vacuum energy, or the energy of this field, it has one component which is just due to the usual energy of an oscillating field, like the electromagnetic field. The electromagnetic field has energies from two sources. One comes from its time dependence, that's the electric energy, and the other comes from its space dependence, its gradients, and that's its magnetic energy. But this field has another form of energy, which is just potential energy. V, can this be seen? I'm writing with blue on blue. No, okay. How about pink on blue? V of phi. So the energy in this field, if I wanted to, I could write it down, and many of you who've done some of these classes would recognize it. There's a term in the energy density which contains time derivative squared. There's another term which contains spatial derivative squared. This is the energy density. It's conventional to put a factor of 2 in there. So vibration of the field, that's this one, gives energy. Variation of the field in space, that's this one, gives energy density. And then one more term, a potential energy, V of phi. And everybody will agree that scalar fields typically do have such potentials. An example would be the Higgs field, which some of you may or may not know about, but that's one which we empirically have good reason to believe in, and that has a V of phi. So V of phi is not an unusual thing or a peculiar thing, but its shape is a little bit unusual and contrived. Contrived meaning to say that you'd have to maybe tune some parameters. V of phi is a function of phi. Well, there are zillions of functions around. Most of them are not very simple. 1 is a simple function. Phi is a simple function. Phi squared is not too complicated a function. Phi cubed is pretty simple. If you start adding things like 1 plus phi squared, you can make some pretty complicated functions. And so it is with V of phi. It's a complicated looking function, meaning to say it's not the thing that you might have written down on your first, in your first calculus examination. But nevertheless, it has to have a shape which looks something like this. It has to be fairly flat over some range. Over some range, it has to be fairly flat. Not absolutely flat. You don't want it to be absolutely flat. You want it to have a little bit of a slope, downward. And then at some critical value of phi, the bottom drops out and it falls away like so. Now, it doesn't quite fall to 0. It falls to something very small, though. And in Planck units, in natural units, what are Planck units? Planck units are units in which c is equal to 1. That's not hard to think about. Planck's constant is equal to 1, and Newton's constant are equal to 1. Those are called Planck units. The units in which the natural unit of length is the Planck length, which is 10 to the minus 33 centimeters. The natural unit of time is 10 to the minus 42 seconds. And the natural unit of mass, anybody know what the Planck mass is? How much? 10 to the minus 5 grams. Right, so it's some units. So some natural units in which the most basic constants of nature are equal to 1. This falls down to something very small, about 10 to the minus 123. That's the vacuum energy today. Up here, it was larger. It was still small in Planck units. We know that it could not have been large on the Planck scale. It was perhaps much, much bigger than this, but much, much smaller than Planck. The universe started. What does it mean to say the universe started over here? What does it mean to say? This is not a place, incidentally. This is a value of the field. What does it mean to say the universe started at this point? When I say started, I don't mean to say that it literally started at that point. I mean to say we can trace it back to a certain starting point, which was more or less like this. And the details of this, incidentally, are not well known. This is more of a cartoon of a situation whose details are really somewhat unknown, but more or less like this. What does it mean to say the universe started at a particular point on this plot? Well, it means to say that the universe started with the field value being something, having some value, filling space. Now, it's not important whether it varied from place to place at this point, because what's going to happen is the universe is going to expand so much that wrinkles in phi will get enormously stretched out. And the region where we sit is deep in the interior of one of these very stretched out regions. And so for practical purposes, we might as well assume that after a little while up here, the universe expanded by so much that our part of it, our patch of it, and perhaps much more than that, was very, very ironed out. Why did the universe expand so fast? Well, that's the Robertson-Walker equation, or the Friedmann-Robertson-Walker equation. And V of phi, incidentally, is something which does not, what's the word I'm looking for? Does not dilute. So it's like vacuum energy. In fact, if V of phi was perfectly flat, it would be exactly the same as vacuum energy. If for some reason the universe just sat at a point, in other words, if phi did not change and it just sat there, then the value of the potential energy at that point would be vacuum energy. So as long as this is pretty flat, the universe will be exponentially expanding with an exponential factor with a Hubble constant, which will be proportional to the square root of this vacuum energy, the square root of V of phi. I'm leaving out 8 pi's and that sort of thing. Let's just put proportional to the Hubble constant will expand, proportional to the square root of V of phi, and the universe will exponentially expand like e to the ht. That will continue, yeah.
What is phi defined on? What's the space? Is it a field on some version of space-time?
Yeah,
But what is?
the field.
But what is that space-time? Do we know anything about that space-time? We don't have Einstein's field equations, right?
Oh, yes, we do.
We do.
Absolutely.
Oh,
This
oh,
is,
just with
that is
everything else
Einstein's
gone.
field equation.
Okay, with everything else gone, okay.
Yeah. Oh, yes. Yes. This is Einstein's field equation. And if we wanted to simplify it, or we would just write for rho naught plus rho matter, we would just write V of phi for the energy density. That's good enough as long as phi is slowly varying. What happens to these pieces of the energy? Well, as long as phi is moving slowly with time, this is not important. And as long as it's been stretched out, as long as things have been stretched out a great deal, then the gradient of phi is small. So these are unimportant, and v of phi is the big thing in the energy while you're up on the top here. Then, of course, you eventually slide down this shallow hill. We can talk about the dynamics of that in a moment. You slide down this shallow hill until you get to the edge, and then plop, down you go. In this picture, cosmology, all of cosmology is a roll from up on the top of a potential, up here somewheres, down to the bottom. Almost everything that we know about, and certainly everything we can observe, happened after the universe plopped to the bottom down here. Okay? With the exception of this exponential expansion, almost all of which, in fact, all of which took place up on the top here. Going over the edge is where the vacuum energy was converted into the energy of particles, radiation, and other more familiar forms of energy, but not all of it. Some little bit of it was left over as vacuum energy. Why? We don't know. We don't know. This is just the picture that emerges from lots and lots of detailed observation. So when the big U went over the edge of the hill here, off the edge of the cliff, that's the place where vacuum energy, this vacuum energy, not this vacuum energy here, but this big vacuum energy up here, was converted into ordinary energy, ordinary things, yeah, including dark matter and other things.
I can't think of any known process, though, that converts vacuum energy into matter energy. Is there one?
Mm-hmm. 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 Yeah. This field, like any other field, has quanta associated with it. When the field rolls down to here and it oscillates back and forth, those quanta have energy. This is a kind of harmonic oscillator. It oscillates back and forth here. The energy of those harmonic oscillators is another way of speaking about the quanta, the energy of the quanta of that field. So when this field, which is called the inflaton, it has a name. Once you name it, you no longer ask why it exists. You just say it's the inflaton. The inflaton field goes over the edge, and it starts ringing down here. It starts oscillating. Those oscillations are another way of talking about the particles, the field quanta, which are the field quanta associated with this particular field. All right? Now, those field quanta may or may not be stable. If they were perfectly stable, that's all that would exist. There would be no way of transferring that energy to other kinds of energy. But typically, the situation with scalar particles, like the Higgs particle or other scalar fields, is they're unstable, and they decay. So one of these particles forming this sloshing stuff here, let's call it the inflaton, can decay. What can it decay into? Who knows? Photons, electrons, E plus, E minus. And that's the way the energy gets converted from the sloshing of this inflaton field into ordinary particles. Now, do we know enough about this field to say that this must happen? No, but we know enough about nature to say that it must happen. Most of the energy in the universe is composed of either dark matter or... One thing this could be, the sloshing around in here, which is a form of energy, could be the dark matter. But we still have to get some of it out into photons and protons and neutrons and so forth. So some decays of this type must have happened. That's the only way to get it to transfer. But you know, there's all kinds of processes that can convert this sloshing stuff into ordinary particles.
So that's happening even today, the conversion of.
Dark matter could be decaying. If in fact this is connected with dark matter, we don't know what dark matter is with precision. Yeah, that could be happening today. Today, in this picture, we're really stuck down at the bottom here. The sloshing ended, but and I'm going to, if I get to it, I'll show you why the sloshing ended.
So what we normally think of as the vacuum energy is really the residual effect of this vacuum energy.
Yeah, yeah.
Do you think there's there may be some connection between the UV IR connection and the?
I don't know. Let's get to an important point here. You might ask if, well, first of all, if you started up on the top here and you fell over the edge, wouldn't you start by energy conservation? Wouldn't you swing back and forth here and perhaps come back up onto the top? Or at minimum, wouldn't you expect to endlessly swing back and forth here? Is there any reason why this energy would get degraded as if there was dissipation, as if there were friction, which would cause this field to slide down to the bottom? Now, think of a mechanical analogy. The mechanical analogy is a particle rolling on a potential like this. Why does it come to rest down here? Does it come to rest down here? The answer is it better come to rest down here, because if it didn't, our universe would be filled with this enormous quantity of energy, and it's not. It's pretty much empty space. How did it get to be empty space? Where did all that energy go? And I'm going to tell you it dissipated. You say, what do you mean it dissipated? Dissipated into what? Well, there's a form of dissipation which takes place in cosmology that doesn't have to do with genuine friction. It resembles friction very much, but it is actually due to the expansion of space. So I thought I would take a couple of minutes and show you where that comes from. To do that, you'll have to recall something which not everybody in the room may know, but it's Lagrange's equations of motion. This is the expression for an energy. Let's suppose that the field did not vary with position in space. Just to make the story simple, let's ignore the gradients of the field with respect to position in space. Why? Because it's gotten itself stretched out so much that this is unimportant. Let's assume that's unimportant. All right, this is the potential energy. This looks like a kinetic energy of something. It's not the motion of a particle, but mathematically, it's proportional to the square of a time derivative. It looks like a kinetic energy of a degree of freedom, which in this case is a field. And this looks like a potential energy. What would be the Lagrangian? This would be the energy. What would be the Lagrangian of such a thing? Energy is T plus V. Lagrangian is T minus V. T stands for kinetic energy. So the Lagrangian is T minus V. Now, actually, this is not the Lagrangian. This is the Lagrange density. You have to multiply it by the volume of space. This was not the potential energy. This was the potential energy density. To get the potential energy, you have to multiply it by the volume of space, right? Same here. This was energy density. So what's the volume of space? Well, A cubed. A cubed of time. So now, if we know how A cubed behaves with time, we have the Lagrangian of this field phi. Okay, let's work out its equation of motion. Do you remember how to work out the equation of motion for Lagrangian? You take partial of L with respect to phi dot. That's A of t cubed times phi dot, and then take the time derivative of that. That's the left-hand side. What about the right-hand side? dv d phi, like a force, like dv dx, like dv dx, except there's the a cubed here. A cubed dv, or dv d phi. dv d phi is the slope, and it's the force term which creates what would be an ordinary acceleration if a was constant with time. But a is not constant with time, so we have a little bit of work to do to take this derivative. To take the derivative, what is the derivative? Well, the first term, the d by dt acts on the phi dot, and that gives us a cubed times phi double dot, which is like the acceleration. Not the acceleration of the expansion of the universe, but it's just the acceleration of this field phi, the second time derivative of phi. That's one term. And what's the other term? The other term comes from differentiating the a cubed. And that's 3a squared of t times what? Times a dot times phi dot. And that's equal to a cubed dv d phi. But I want to divide both sides of the equation by a cubed, just to get rid of as many a cubeds as I can. All right? So on the right-hand side, I'll just have dv d phi. And on the left-hand side, I'll get rid of this a cubed. I'll get rid of a squared, but it will leave me with a 1 over a in the denominator. So let's put 1 over a dot over a. What's a dot over a? It's another name for it. Not the square root of h, it's h. Right, just h. So this is the Hubble constant. Now, have you ever seen, oh, this is minus. There should be a minus here, minus dv d phi. Yeah, minus dv d phi. Force is proportional to minus the derivative of the potential energy. Have you ever seen an equation of motion with a single phi dot in it like that? Viscosity. Viscosity. A ball or a rock falling through water. This is essentially the equation of motion of a rock falling through water. Here's the gravitational force on it, dv d phi, and it's proportional to the slope here. Here's the acceleration, and here's the viscous drag force. Here's the viscous drag force. So, believe it or not, this is called Hubble friction. Hubble friction. It's not real friction. It's due to the time dependence of the size of the universe. That's where it came from. It came from differentiating A, but it resembles very, very closely the equation of motion for an object moving through a viscous fluid. And if V has a more or less uniform slope, it's like an object falling through a viscous fluid under the presence of a uniform force. What happens under those circumstances to the falling object? It comes to some terminal velocity. It comes to some terminal velocity very quickly. You drop a rock in water and it very quickly comes to terminal velocity. So the universe starts sliding down this hill. If this is shallow enough, it goes very slowly down the hill here. And as it goes down the hill, viscous friction, or Hubble viscosity, or whatever it should be called, Hubble damping, brings it very quickly to a terminal velocity, and it just slides down this hill slowly till it gets to the end. During the time that it's sliding down the hill, well, sliding down a hill which is of very, very shallow nature, there's some vacuum energy, and that vacuum energy causes almost exact exponential expansion. When I say almost exact, it's not exactly, because there's some slope here, so the vacuum energy changes from one time to another. But if this is reasonably flat, the universe will grow exponentially, approximately, with a constant h here, and then it will come to the end and fall down. And How many times does the size of the universe double? Well, that depends on how shallow this is, how broad it is, and how high it is. The height of it goes into the coefficient here, goes into the time constant here. The width of it and the slope of it determine just how long it stays up on the top of the hill there. So by making it broad enough and flat enough, you can make the universe expand as many times as you like during this period of inflation. Okay, so then you would say, if it exponentiates by many, many, many orders of magnitude, why doesn't that iron out all of the variation in the field? Why does it have any variation at all by the time it gets over the edge here? What is that variation? That variation is that small little bit that's necessary for galaxies to form. So on the one hand, you've explained the flatness of the universe and the homogeneity, but it looks as though you might have overdone it. You might have overdone it and lost the possibility of explaining the existence of galaxies. Now, marvelously, that's not exactly right. So, to understand why it's not exactly right, we have to take some things from quantum mechanics. Let's suppose that the universe was not expanding, and just the simplest possibility. Let's forget the expansion of the universe for a moment, but let's add quantum mechanics to this picture of a field filling space, where the field, because of the expansion, but we're going to forget the expansion, but because of the expansion, the field has gotten extremely ironed out. So it's almost perfectly homogeneous, but quantum mechanics makes it fluctuate. Quantum mechanics makes it fluctuate. One way of seeing the fact that quantum mechanics makes it fluctuate is just by looking at the similarity of the field of its energy plus V of phi, by looking at the similarity of such a field with the motion of an ordinary particle. This is like kinetic energy, and there's some potential energy over here, plus another term over here. Why is it? It's kind of like a harmonic oscillator. This V of phi could conceivably be a harmonic oscillator potential, but there's also a harmonic oscillator potential in here, hidden in here. Why is it that harmonic oscillators have zero-point energy? They have zero-point energy because of the uncertainty principle. You cannot have phi being fixed and locked and at the same time have the velocity of phi be fixed and locked. It's the uncertainty principle. The uncertainty principle, in the same way that the uncertainty principle tells you that there's zero-point energy of a harmonic oscillator, ground state energy, whatever it's called, the same mathematics tells you that phi is necessarily, even in its ground state, even when all the energy is sucked out of it, it's still oscillating with zero-point energy. So that means if you were to look microscopically at this field, you would see it constantly in a state of agitation, even just in the state of absolutely lowest energy. Okay, why don't we notice those fluctuations? And for the most part, we don't notice them because they're too rapid. They take place too rapidly for most observations, and we average over them. Okay, we average over them. Most such fluctuations are fairly short wavelength, and the short wavelengths oscillate very fast. And because they oscillate fast, we don't notice them. But in cosmology, the situation is a little bit different. And to understand how the situation is different, you have to take into account the expansion of the universe. That's the main new thing, the expansion of the universe. Okay, let's draw the universe. Horizontal is space, as always. Vertical is time. and x goes horizontally. X is the coordinate x. It doesn't measure distance. It measures coordinate along here. Here are the various galaxies, for example. I'm putting them equally spaced, which of course they're not. And of course the world is three-dimensional, not one-dimensional. But these are the galaxies. I've approximated them by saying they're equally spaced, and they're just vertical lines. But the distance between galaxies is not the difference in x, but what is it? AX, A being scale factor. So distance is A of t times delta x, where delta x might be the distance in coordinate between 2 points. So if A is so let's imagine now that A is exponentially expanding, e to the ht times delta x. That means the distance between galaxies, on the average, if they're far enough apart, is expanding exponentially. Delta x is, of course, not expanding exponentially. Delta x is just the fixed coordinate positions of the galaxies. You can think of it as their names. But it's the scale factor which is increasing exponentially. Now, what happens to a wave in here? What happens to a typical wave as the universe expands? It gets stretched out, but in these coordinates it's not stretched. In these coordinates it stays more or less the same with time. It has a fixed wavelength in x, but that means an exponentially growing wavelength in proper distance. The proper distance. So the wave more or less has the same profile. It may be oscillating, but it's not expanding on this diagram, because this diagram already has the expansion built in as the expansion of the distance between these points. Okay, but it oscillates. The field oscillates. In general, it oscillates, unless its wavelength is too long. If its wavelength is too long, it doesn't oscillate. So let me explain why it doesn't oscillate. Supposing we have, why does a wave oscillate, first of all? Why does an ordinary electromagnetic wave oscillate? Think of a rope stretched between 2 points. And perhaps the rope has some curvature over here. Maybe it does, maybe it doesn't. Let's just, may have some curvature, may not. Why does the rope over here get pulled down? It gets pulled down by its neighbors, by the neighboring segments of rope, which would typically be down here. But what if the neighboring segment of rope was up here? Which way would it get pulled? Up. All right. So the only way to know which way it's going to get pulled is to know what the neighbors are doing. In particular, well, yes, to know what the neighbors are doing. But supposing the size of the wave here was about as big as the horizon. About as big as the horizon. Remember what the horizon is. The horizon is distance beyond which things are moving away from you faster than the speed of light. You can never get any information from beyond the horizon. That's a principle. Nothing can communicate from behind the horizon. So here's a piece of rope that if the scale is big enough for the variation of the position of the rope, one could imagine that, that this piece of rope is out beyond the horizon. Supposing this piece of rope was out beyond the horizon, can it have any influence on this piece? No. No. So it better be that the tendency to pull on this piece of rope, or this piece of field, this little piece of field in here, that had better be tremendously diminished when the wavelength of the wave becomes about equal to the size of the horizon. When the wavelength is longer than the size of the horizon, then the pieces which are pulling on a piece over here are out beyond the horizon. And the answer is, if you follow the mathematics, that when waves get longer wavelength than the size of the horizon, they freeze. They're not pulled back by the neighbors, and they just freeze. Their motion becomes frozen. All right? Why should I worry about waves? I'm worried about quantum fields. My goodness, what are we talking about? Waves longer than the size of the horizon. Well, the point is that the universe is expanding. So take a wave of a certain wavelength and push it ahead in time. On this graph, it has the same wavelength, but the distance between these points exponentially grows. So no matter how small the wavelength is to start with, eventually, as the universe grows and stretches, each hidden wave, each zero-point oscillation, will eventually have a wavelength longer than the size of the horizon. When that happens, the wave stops oscillating. It just stops oscillating, it is no longer pulled back, and it freezes. It just freezes. Okay? So if we wait long enough, let's suppose this wavelength here is, I don't know, 10 to the minus 8 centimeters, some small wavelength. And it's oscillating like mad because it's being pulled back into place by its neighbors. But as time goes on, this 10 to the minus 8 centimeters grows to the point where it may be as big as the horizon, will be as big as the horizon. When that happens, all of a sudden, the wave freezes. So the zero-point oscillation in an expanding universe, in an exponentially expanding universe, the zero-point oscillations become frozen. First, the longer wavelength ones become frozen. All right, so eventually, this wave over here will become frozen. But then, what about shorter wavelengths? Shorter wavelengths will take a longer time, but they will also eventually become frozen. Even the very shortest wavelengths that you can imagine will eventually become frozen. Yeah?
If you do the horizon distance on the origin on that graph, would it kind of asymptotically go to the vertical axis?
Yeah, that's a good point. All right, so let's draw what the horizon would look like. Yeah. The horizon, what is the horizon? The horizon, let's work out what the size of the horizon. The horizon is a distance that corresponds to the speed of light using the Hubble formula. All right, so it's velocity, distance, I always have to work this out. Distance is, velocity is equal to Hubble times distance. The distance at which, this is the speed of light, that's called the horizon, and that distance, therefore, is the speed of light divided by the Hubble constant. That's the distance that corresponds to the distance to the horizon. Right? So that's the distance to go. What did you ask me? You asked me a question.
Doesn't it,
Oh, yeah.
approach the
Right,
vertical axis?
right. Yes, it does. The distance is a fixed number. The distance to the horizon is fixed. It's just c over h, and in an exponentially expanding universe, h is fixed. All right, but the distances on this graph are exponentially increasing. So a fixed distance on this graph looks smaller and smaller. A fixed distance of Hubble size, this is called Hubble size, this distance here, would look smaller and smaller because it's being compared with exponentially growing distances. So that means that the horizon size would look like this. Exponentially getting smaller and smaller with time. And that's why each wave will eventually, it's frozen, becomes frozen when its wavelength gets longer than the horizon size. Okay? Or when the horizon in coordinate distance has shrunken to be smaller than the... Right. Okay, so each wave gets frozen, and they pile up on top of each other. They pile up on top of each other, each one frozen, and what was originally quantum fluctuations very rapidly oscillating become large-scale fluctuations of the field which grow and which pile up on top of each other and which just freeze. Okay. At the end of this, by the time you get to here, all these waves have piled up and made some sort of variation in the field, some sort of frozen variation in the field. And so the next question is, when this field, which now varies from, and notice, it does not matter how long it's been inflating. It could have been inflating so long that the universe is 10 to the 10 to the 10 to the 10 to the 10, and we go on all night. That's how much bigger it is. That's how much it would be ironed out. But nevertheless, as time goes on, new fluctuations get frozen. New waves become frozen. More and more of them become frozen. And so the end result is there's always a variation that's kind of the fossil remnant of early vacuum fluctuations that got frozen into the system. And they get frozen in, pile up on top of each other, and become a large-scale, massive, macroscopic variation of the field. Yeah?
What happens to the amplitude as it gets bigger?
What happens what?
The amplitude of the fluctuation, is it scaling down?
Yeah, it's scaling down. It's diluting at the same time. Its energy density is diluting as it expands. So in fact, I mean, it doesn't get out of control from the point of view of energy density, but it just keeps making, you know, more oscillations, piled up on more oscillations, and the effect is a kind of stationary, steady state variation. That's yeah.
That's what I was going to ask. You get to a steady state
Yeah.
where as time goes on, you erase the earlier.
Well, you stretch them out.
You stretch them out, and
Yeah,
so you can't.
and new ones keep coming in.
And new
Right,
ones keep coming
right.
in.
You stretch them out so that they're bigger than the
So
horizon.
if you look
Yeah.
at it at one time and look at it 2 hours later or 2 years or whatever the hell it is,
Right,
it looks the same.
right. That's called a scale invariant spectrum. Scale invariant spectrum. And one of the things that has been known about the initial...
Just by something you said, it seemed like you were saying that the older fluctuations were ossified by being frozen.
Right.
But it sounds like what you're really saying is...
Well, they were ossified first.
Not only were they ossified, they were spread out. I
They
mean,
were ossified and then stretched.
But they're not seen as fluctuations or because the wavelength is so long, but they're over there. I mean, they're beyond the horizon.
Okay. Remember, there was the horizon. There were two different horizon scales. There was the horizon up here, and there's the horizon down here. The horizon up here just means the distance scale associated with the vacuum energy in here. Okay? The Hubble scale down here means the distance scale associated with this energy density. They're very different. 110.
So there's a small horizon up
Right,
there.
a small horizon up here. All right, these waves become ossified when they move during this era. The waves get ossified when they get bigger than the horizon associated with this energy scale. This could be some microscopically small thing from our point of view. Right?
So
Then they get frozen.
Seen as fluctuations even though they're frozen.
They're frozen.
At a point where it's actually far enough away that when we get a small,
Yeah.
our horizon grows, we can actually see it.
That's right. That's right. Our horizon grows. What happens at first is that these waves get bigger than the temporary, it's really a false horizon, but a temporary horizon over here. But then the horizon grows. When it rolls down here, the horizon suddenly turns that way, and these waves come back into the horizon and they start to oscillate again. They start to fluctuate again. But by that time, they're stretched out on enormously large scales, and they're piled up. So you have a huge pile up of waves, macroscopic structures, and those macroscopic structures start to slosh around again. In fact, that's really what happens. They start to slosh around again. The words we use is they go out of the horizon and come back into the horizon. So they expand out beyond this temporary horizon and then get swallowed up by the larger horizon, at which point they start to slosh around again. Right. But as I said, by the time they start sloshing around again, they're big, macroscopic,
Take a long time to swing.
right, and take a long time to swing.
All that, when the field was flat up there, all those e-foldings occurred in really a very small amount of time.
Well, we don't know how long.
Well, let's just say, take the example last week, like you say maybe 60 e-foldings.
Oh, that would be very, very small amounts of time. I mean, by macroscopic standards, yes, very, very small.
How did it, I don't know if you can answer this in the timing name, but how did you calculate the power spectrum that you get? How do you?
Well, just from this picture, just from this picture, that the waves keep different wavelengths, keep passing out of the horizon, but at each stage the same thing is happening, exactly the same thing is happening as the previous stage. And it's on a logarithmic scale. One can calculate it and see that at each stage it looks the same, except everything's scaled up, and it reaches this sort of stationary phase. That's a little too complicated to go into. But it does achieve this scale invariant behavior where the same, more or less the same amplitude of oscillation for every wavelength. That's not exactly true, but close to it. And the result is a particular structure of frozen-in density variations. Okay, now let's go a little bit further and talk about what happens when you go over the edge here. When you go over the edge, those fluctuations get magnified. Not magnified in spatial size, but magnified in amplitude or in energy density. The energy density, the energy variation from place to place gets magnified. And it gets magnified proportional or inversely proportional to how slowly the field, inversely proportional to how fast the field was rolling down here. The flatter it is, the smaller the terminal velocity as it's rolling down here. The smaller the terminal velocity, you might think this is a little bit counterintuitive, but the smaller the terminal velocity, the bigger the variation in the energy density will be after you fall off the edge here. So let me just show you why that is. I talked about it a little bit last time. I was a little bit tired last time, so let me just say a little bit more about it. Okay, so the field is varying from place to place because of these quantum fluctuations. Let's say to the right is red and to the left is blue. Then there will be regions which are redder, regions which are, let me use green. Here's green back here and red over here. So there will be greener regions and red regions, and green regions and red regions. Now, I don't really mean back here and up here. I just mean small deviations from here to here, small fluctuations. This is an effect that has to be fairly small. Otherwise, it would just have created too much random mess in the universe. So it's a small effect. But there are greener regions slightly to the left and redder regions slightly to the right. Naturally, the redder regions fall off the edge before the greener regions. Okay? Supposing a little red region over here falls off the edge of the cliff. It falls off the edge of the cliff, and all of this vacuum energy, let's suppose all of it for simplicity, all of it got converted to radiation energy. That's a simplified story. But let's suppose it just got all turned into photons and so forth. So let's see, the redder region because it was a little bit ahead, moving toward the edge of the cliff, it got there first and fell off the edge. So this redder region would have all of its energy turned into a kind of energy which dilutes with expansion. The greener energy, which is still up on the top here, is still vacuum energy. It does not dilute. Okay? So what happens to the energy density in here? The energy density in there decreases. It decreases just by the standard rules. By the time you're down off this cliff, you're in a world now which is pretty much like ordinary cosmology. Right? Ordinary material, radiation or whatever. If it were radiation, we know the energy density in there would go as 1/8⁴. The scale factor in that region, or the expansion factor in that region, would be growing, and the effect would be that the energy density in there decreased. Okay. What about the energy density in the greener region after it fell off the edge of the cliff?
It would be higher than the red.
It would be higher because it fell off later. So by the time a bit of green energy goes over the edge, the red energy has already been redshifted. It has already been redshifted or diluted by expansion, whereas the greener regions are not yet diluted. But if you wait a little more, the redder regions will get even more diluted, the green region will start to get diluted, and the even greener region will come and fall over the edge and make a yet higher energy density region. All right, this is the way that, and what is this effect proportional to? Well, the slower the average motion, the longer the time scale between different pieces falling over the edge. If everything is moving extremely slowly, even if one point is slightly ahead of the other here, if it's moving extremely slowly, there will be a large gap in time between the time the first piece rolls off and the time the second piece rolls off. That means that the red energy will get highly diluted by the time the green energy falls off. So the flatter this is, and the slower it moves, the larger will be the variations in the energy density from place to place. The final upshot is a spectrum of fluctuations of energy density, which is the remnant of all of this, which depends. It depends on the height of this. It depends on the width. It doesn't depend much on the width, but it depends on the slope a little bit. Why the slope? Because the terminal velocity depends on the slope. And the slower the terminal velocity, the bigger will be the fluctuations. Doesn't depend much on the width. Right. So for that reason, we can't say how many E-foldings took place. But it depends on the height and the slope in such a way that the shallower the slope, the bigger the fluctuations. Also, the higher it is, the bigger the fluctuations. The higher it is, the more energy density, the larger will be the fluctuations, and the flatter. And there's a formula that you can work out that will tell you how big the fluctuations are. But the point is that the detailed result of such an analysis fits extremely well with empirical data.
So what's the height and slope?
No, unfortunately, you cannot tell what the height and slope is. You can only tell a combination of the height and the slope. There's one combination of the height and the slope that you can predict. Okay. And, well, okay, that's not quite true. Okay, not quite true. If the height is high enough, then there are, in addition to the production of these density fluctuations, there are production during the gravitational era here, or during this inflationary era, there are also gravitational waves produced. And so admixed into this density fluctuation and the temperature fluctuation on the sky, there may be also gravitational waves that are visible. If there are gravitational waves, that will tell us how high it is. But if it's too low, then there won't be visible gravitational waves, and that's possibly the case, very likely the case. So it's going to wait until the gravitational waves can be detected from this period, and that will give us some idea of how high it is. Most likely it will just tell us it's lower than a certain amount. If the energy density were any bigger, I'll tell you if in Planck units, if the energy density were bigger than about 10 to the minus 14th, which may sound small, but it's a huge energy density, bigger than about 10 to the minus 14th, then we would have already been swamped by gravitational waves from it. So we know that the energy density is less than 10 to the minus 14th because we were not swamped by gravitational waves. On the other hand, if it's less than about 10 to the minus 16th, then we have no chance of seeing the gravitational waves. And so there's a narrow little window, which we have no reason to believe is something like that, I think. Narrow little window where you could see gravitational waves. 10 to the minus 14th might actually be 10 to the minus, I don't remember the precise numbers, but it's in that ballpark. There's only a narrow region of parameter space where you could see these.
Is the units the Planck mass over the Planck volume? Is that what we refer to 10 to the minus 6 and 16th and so forth? What units are those referred to?
Mass to the fourth. Mass to the fourth. Yeah, why is it mass to the fourth? So let me explain why it's mass to the fourth. First of all, if you set C equal to 1 and H bar equal to 1, those are natural things to do, then mass is the same as inverse length. All right, mass is the same as inverse length. So let's just, mass and inverse length are the same thing. What did you ask me? I forgot. Oh, what are the units of the energy? All right, it's energy density, first of all. Energy density. So it's energy divided by length cubed. And if 1 over length is the same as energy, then it's energy to the fourth. Okay. So it's m Planck to the fourth that are the units. Right. And empirically, we know from the lack of gravitational waves in the spectrum of, in the cosmic background spectrum, that it's less than, maybe it's 10 to the minus 12th, I don't remember exactly. But, and the problem is that if it was another decade or two smaller than that, you would have no chance of seeing it. So you're caught between being swamped by it, well, you're not swamped by it, and in a couple of decades down, and you couldn't see it.
The swamp might mean it would affect our cosmology in a major way.
Oh, yeah. Yeah, we would have seen a lot more structure in the microwave background. Yeah. Yeah.
Due to the successive freezing out of these long waves in pi, shouldn't pi be undergoing a random walk?
Yeah, it does undergo a random walk at any point. At any point, it undergoes a random walk. It's exactly what it does. But of course, it undergoes different random walks at different places, and that's what makes the variation. It's a statistical process. That's exactly right. So if you focused on one particular point in space, you would see one mode freeze out, and the next mode freeze out, the next mode freeze out, with random phase between them, and it would make a random walk. That's exactly right.
So the question that preoccupied people for a long time, which is what happened at t equals 0, is irrelevant. There is no t equals 0.
Well, irrelevant or not, well,
I mean,
no.
There is no t equals 0 in this model.
Okay, so the,
Back in time.
right, well, let's put it this way. The success of this theory, and it has been highly successful in correlating a lot of data on different wavelength scales. When I say it correlates lots of data, it correlates data about fluctuations on very different scales. Scales comparable to the whole size of the sky, variations across the sky, which are large scale down to very small scales of 1,000 times smaller than the size of the whole sky, And it correlates all those fluctuations, density fluctuations, basically into one set of parameters governing this potential here. So in that sense, it's highly successful. The upside of it is it washes out whatever the initial conditions were, because this stretching washes out what came before, and only the quantum fluctuations which are produced later are relevant. So the success of it is that it washes out what came before, but what's one era's success becomes another era's disaster. It means now that we accept all of this and we all think it's true, next thing we want to know is what happens earlier. And all of the things which made this a very successful theory work against us in finding out what happened earlier. So inflation, when it occurs, tends to wipe out the past. And as I said, that's both good and bad, particularly bad for those who want to understand what might have led up to this. The point is, this is a ridiculous starting point. This energy density, while it's easy to accept that the universe might have started with a very high energy density. That's easy to accept, big deal. The problem is the energy density was very, very high in ordinary units, joules per cubic meter or whatever. It was enormously high energy, even on particle scale units. Much higher energy density than, for example, the density of energy inside a proton. So it was enormously high energy. On the other hand, it was very small in any natural units. It was 10 to the minus 14th or something, or 10 to the minus 12 or smaller. So it's neither here nor there, so to speak. It's neither very big nor very small. It doesn't sound like it's the sort of place that natural starting point would be. Natural starting point might be with the energy density, for example, being Planckian, being 1 unit in Planck units. 10 to the minus 13 or 10 to the minus 14th doesn't sound like it's the starting point. Now, of course, that could be wrong, I don't know. But there's no natural explanation of this whole structure and why we might have started over here, and whether or not we might have tumbled down from some much, much higher energy density up here. That's all lost. That's all experimentally lost because inflation just stretched things out so much that we lost it.
Could it be that there was no start? I mean, it just continued, went down to the point. If it's exponential, there isn't a real start to it.
Could the exponential have gone on, you mean, into the remote past? No. 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 No, this is an extremely odd story. You say, what would have happened if the energy density was absolutely constant out here, for example? Well, this function has to do something. Right? It could increase in this manner here, in which case it would say in the remote past something different was happening than down here. Okay. Exactly what was it? Well, we then go up to here and we say, could there have been a plateau up here that went on and on indefinitely? Well, we might as well say, could there have been a plateau over here that went on and on indefinitely? All right, so what are the consequences then of a universe with an absolutely constant energy density like this? Suppose we're way out here with an absolutely constant energy density. Well, when I told you that de Sitter space was an exponentially expanding universe. That is correct at late times. In fact, real de Sitter space is a universe which looks like this, which contracts and then expands. That's the real honest solution of Einstein's equations with a cosmological constant. It contracts and then it expands. It contracts to some minimum size. That minimum size happens to be the Hubble scale. And then it starts expanding. And it expands exponentially. I wrote that the scale factor was like the exponential of ht. That's not exactly right. Can you think of a function which contracts and then expands and at late times looks like exponential? Hyperbolic. Hyperbolic cosh. Yeah, cosh ht. That's the real solution of Einstein's equations. So the real solution of Einstein's equations is not an eternally exponentially expanding universe, but it's one which contracts and expands. Now, should we believe, the question comes up, should we believe in this contracting phase? All right. Should we believe in the contracting phase that came before the expansion? I will just leave that as a question mark. I will leave that as a question mark. Or should we believe that somehow we started in some other way, unknown? I think down here, mystery down here. We don't know very much about that. We really don't have a theory of the beginnings. If this plateau really gave way to a much higher mountain here, it would mean that this might have started much smaller. In fact, if it gave way to a mountain which is as high as the Planck scale, we might even want to say it started as the smallest possible thing, 1 Planck length on a side. The fact is, we don't know. We don't know very much about any of this.
We're never going to find out.
No, why did you say that?
Because it's all erased, it seems.
Well, it just means you have to be clever.
Huh?
Yeah, it's of course all erased if there was too many e-foldings.
Yeah.
Right. If we are very, very lucky, and there was 63 e-foldings, then we have a chance of seeing it. We have a chance of seeing some of this.
I'm trying to think out what the Hubble damping does to the field equations. In particular, does that change the quanta of the field equations as time goes on?
What it is it's the redshifting of the field quanta. It's equivalent to the redshifting of the field quanta. In other words, it appears that energy is being lost, but one way of thinking about it is the energy is just being stretched. So it's completely equivalent to the redshifting. So.
Yeah, you mentioned in passing that mass is the inverse of length. Yeah. You mentioned in passing that at small scales, length is the inverse of mass is the inverse.
The units of length and mass are inverse to each other. The formula, for example, for the Compton, what's the formula for the Compton wavelength, the quantum mechanical wavelength of a particle of mass m? Compton wavelength lambda Compton. Anybody know? It's got an h bar in it. It's quantum mechanical. Well, over momentum, but we're talking about now a particle of a given mass, so it has to have units of mass times velocity, m times c. H bar over mc is the Compton wavelength. So we know that h bar over mc has units of a length. Now, if we work in units in which c is 1, which we've all gotten very used to by now, and if we're also quantum mechanically inclined, we might also set h bar equal to 1. We don't have to. We can just say that lambda is inverse to a mass. But if we do set h bar equal to 1, which is a common thing to do, then wavelength has units of 1 over mass. So length has units of 1 over mass. Mass has units of 1 over length.
When these waves get stretched out and they become frozen, the frequency goes to 0, obviously. So wouldn't that mean the energy goes to 0?
Yes?
And they still exist even though they have 0 energy?
Well, they're continually being, as this process goes on, waves become frozen, they become stretched, their energy is degraded, and they're replaced by new ones. But the net effect, as it was pointed out, was a kind of random walk where the field just becomes a statistical noisy mess. And on every scale, and every length scale. So what's depleted by the expansion gets replaced by new waves coming in and freezing in on top of those previous ones.
Is that like the slowing down of coordinate time when you approach an event horizon?
Which?
Well, like when you approach an event horizon of a black hole.
Yeah.
You get a more and more red shifting, and meaning then that like
It's connected with that.
connected with it.
It's yeah, it is, but yeah.
Is there any way to make sense out of a question of how probable inflation was, in a sense of looking at various parameters for the space?
Yeah. There's a space of parameters. The first order, not first order in any technical sense, but the first order in thinking about it, there's the width of this, there's the height of it, and there's the slope of it. The slope. Remember, the slope comes in a prominent way because the smaller the slope, the slower the field moves, and the slower it moves, the more, the bigger the fluctuations. These are three parameters. The height, let's call it V naught, the height of it, the slope of it, and the width of it. I don't know, delta phi. Now, generally speaking, most physicists are of the opinion, delta phi incidentally has units, and it has units of mass. Generally speaking, physicists get very uncomfortable when a thing with the unit of mass gets bigger, a fundamental thing, becomes bigger in mass than the Planck mass. They get very uncomfortable about that. And most of us would probably maintain that the scale of variation of a field like phi should never be bigger than about 1 unit in Planck mass. That may or may not be true, but if it's true, it tells us one piece of information. Another piece of information is that the energy density should never be bigger than 1 in Planck units. That's something we really believe. I won't get into the reasons for it, but that's, there's a lot of reason for that. And so having some kind of bounds on these, we're really talking about bound on the slope here. We're talking about what's the probability that the slope is shallow enough that 62 e-foldings happen, or 60 e-foldings happen. What's the probability? And the answer is about 2%. That you have to adjust this slope to about 2% in order to get it to roll slowly enough here to get the required number of e-foldings. All right, is 2%, is that, how unlikely or how likely is that? Well, it's 2%. Now, there's another interesting element to it. There is another, but I won't have time for it, so I'm not going to try to get into it. There is another element to it. The other element, well, no. The question is inflation, we would need to get into issues of anthropic questions. We have two puzzles, cosmological puzzles. Both of them are fine-tuning puzzles. One of them is a mild fine-tuning. It's only 2% in some way of thinking about it. It's only 2%. The other is the fine-tuning of this 10 to the minus 123 down here. They're two big fine-tuning puzzles. Both of them can be resolved in one simple explanation, whether you like it or not, that the universe had to be such that structure formed in it, structure, meaning galaxies, stars, planets, and so forth. And here's a way to think about it. A positive cosmological, let's take a particular case. Positive cosmological constant, an open, negatively curved universe. Let's take that as our model. We could take any other combination we liked, we'd get the same answer. But let's take positive cosmological constant, an open universe. Okay, so what is a positive cosmological constant from a Newtonian point of view? From a Newtonian point of view, it's a repulsion. It's a repulsion, a repulsive force, a universal repulsive force, which is proportional to distance. That's what a cosmological constant is. If we went back to the Newtonian description of things that we started with in the very early part of the quarter, and added into the usual Newtonian gravitational force between objects another term which was proportional to a thing called lambda times the distance between objects, that would mimic the cosmological constant. And a positive cosmological constant, which is what we see, would correspond to a universal repulsion. But because it increases as a function of distance, it had better be small. It better be small enough that it doesn't affect the solar system. In fact, it better be small enough that it doesn't affect the galaxy. In fact, it better be small enough that it doesn't affect seriously big clusters of galaxies. And in fact, experimentally, it's known to only be important at the scale of that 10 billion light years. So it's a very small repulsion. But what would happen if it was 100 times bigger? 10 to the minus 123 is how big it is. Right? It's because it's so small that it only has an effect on... incidentally, what if it was 10 to the minus 10? That repulsion, yeah, it would be easily enough to blow apart an electron. What if it was 10 to the minus 100? Easily big enough to blow the Earth out of easily, by many orders of magnitude. All right? So what if it was 10 to the minus 121 instead of 10 to the minus 123? Well, not galaxies today. It would not be potent enough to blow up the galaxies today. But it would be potent enough to prevent this 1 part in 10 to the 5 fluctuations from condensing into galaxies. So this very mild variation that was there, left over from inflation, it would only take a little bit of universal repulsive cosmological constant term to prevent it from condensing into galaxies. This was Stephen Weinberg's discovery in 1987, that a cosmological constant roughly 2 orders of magnitude bigger than the 10 to the minus 123 would have prevented galaxies from forming. At the time, it was thought that the cosmological constant was 0, and he said, no, there's no reason for that. It just has to be small enough to allow galaxies to form. And he was right, that experimentally it wasn't 0. It was just small enough to allow galaxies to form. Okay, there's a similar logic that goes with the curvature of the universe. Let's take the case of negative curvature. Do you remember what K means from the Newtonian point of view? Or in particular, K being whether you're positive, negatively, or 0 curved. It had to do with the energy of recession.
Escape velocity.
Escape velocity. K equals 0 meant everything is moving with exactly the escape velocity. K greater than 0 would mean, K greater than 0 means less than the escape velocity. K less than 0 means greater than this. So if we take the case of K less than 0, which for one reason or another has become the favored case, but it wouldn't really matter. If K were less than 0, it would mean that everything was shot out with greater than the escape velocity. Okay? Well, that sounds bad. It sounds like too much velocity can also prevent galaxies from forming. 2 things can prevent a rock which are going out from returning. One of them is if you're above the escape velocity. The other would be an additional outward force that you didn't know about, which might have been proportional to distance, but very small. Okay? Both a positive cosmological constant and negative curvature would both work in the direction of preventing galaxies from forming. Now, the cosmological constant is very small. What about the negative possibility of negative curvature? If the universe is slightly negatively curved today, it was much more negatively curved in the past, right? Because curvature, radius of curvature gets smaller, so it's much more negatively curved in the past. We go back to the past when galaxies form and we say the universe must have not been too negatively curved. What could have caused it not to be negatively curved? If it started out negatively curved, what can dilute curvature?
Inflation.
Expansion. Curvature. Inflation. Inflation. All right? So you can say how many e-foldings of inflation had to take place in order that the universe flattened itself out enough before this aero and structure was formed. How many e-foldings had to have taken place in order that the outward thrust of things didn't prevent galaxies from forming? And the answer is about 59.5 e-foldings. We know that there was at least 62. We know that for us to be here, it had to be more than 59.5. All right? So one explanation then is that we can just throw away the possibility that there was less than 59.5 e-foldings. Okay? And then we can ask the conditional probability. What's the probability, given that we're here, to ask the question? In other words, given that there were more than 59.5 e-foldings, then we can ask what's the probability that there was more than 62? In other words, we can take this parameter space and we can say, let's cut out all the parts of it where there weren't enough e-foldings, enough expansion to get rid of the large outward thrust which would prevent galaxies from forming, throw it away and ask with the remaining part of the parameter space, given that there were more than 62 more than 59 e-foldings, what's the probability that there was more than 62? And then the answer becomes maybe 0.9 or something. So it depends on how you ask the question, what the probability of inflation was. If you ask the question conditional that we're here to ask the question, then the answer is that it's very probable. If you ask the question from a more a priori point of view, what's the volume in the parameter space, then it's less than 2%. So it depends on how you ask the question. The same is true for the cosmological constant. If you ask what's the a priori probability that a number is less than 10 to the minus 123, well, it's 10 to the minus 123. But what's the probability that, that if we're here, then the number becomes of order 1. So these are the great puzzles. These are the great confusions, the great puzzles, the great debates which are going on. And that brings us to the end of the great debate.